NPTEL course, Geology and Soil Mechanics. So today we are at the end of this course, and in today's session, we'll first make a quick summary of the topics which we have learned from this course, Geology and Soil Mechanics, and then we'll take a few selective problems from the recent GATE examination 2024. Okay, so this is a kind of outline for today's session. So therefore, uh, if we try to make a quick summary of this particular course, so then we have to begin with the description of soil, engineering geology of soils and their formation, and index properties of soils, which we learned in the very beginning, that is in first week of this session of this course. So under this topic, these headings, that is description of soil, engineering geology of soils and their formation, we have mostly seen that what is soil, how they are formed, and typical soil deposit in various parts of India. Okay, so which are mostly encountered or which are mostly seen by different uh, investigation reports. Then we started learning the very basics of this course, that is index properties of soils. So as you know that soil is a three-phase relationship. So it contains solid particles, it contains water, and it contains air. So in the solid, so these are the different uh, particles particles of different size and shape. And coming to the air and water, so they are basically stored, or they basically form the pore matrices. Okay, so the pore, which are basically inside the soil particles, so that basically filled up by they are basically filled up by air or water. So depending on the volumetric fraction, so we can differentiate the phases of or different conditions of soil. So for example, if the pores are completely filled up by air, that is there is no water inside the soil matrix, then we can say the soil is in dry condition. While in the reverse case, when the pore structures or the pores which are inside the soil matrix are completely filled up by water, that means there is no air, we can say that the soil is under complete saturated condition. Okay, so depending on that, we have also seen different types of unit weights that can be possible for a soil matrix, starting from bulk unit weight, which is quite natural. So the pores are partly filled with air, partly filled with water. So it is termed as the bulk unit weight, then the dry unit weight, and saturated unit weight. Okay, so there is one more unit weight what we have seen from this course, that is submerged unit weight. Okay, so it's a basically it's a difference between saturated unit weight and unit weight of water. Okay, so we'll not go in much details about all these contents. We'll just make a brief review of all the pertinent aspects or the important aspects which we have covered through this course. Okay, now once this index properties of soils, which we have basically learned from this course, we proceeded further and we entered into another chapter of this course, that is classification of soils and clay mineralogy. Okay, so it's also very important. So far uh, you are familiar with these terms, classification of soils and clay mineralogy. So why classification of soils is needed, and what are the different types of classifications reported in the literature, and how to classify the soils. Okay, so what are the basic steps which are involved in the classification of soils? So for this course, as per the scope of this course is concerned, we were confined to the Indian standard classification system. So subsequently, we have solved a few problems, how to classify, where the index properties means this liquid limit, plastic limit. So these are the Atterbuck limits, and apart from these are required to classify a fine grained soil. Then for classifying the coarse grained soil, the sieve analysis, hydrometer analysis data which are required. Okay, so that we have seen from week 2. Now, coming to the soil compaction, which is a process of densification of a soil matrix by expulsion of pore air through or by means of imparting mechanical energy. That also we have seen, and it's quite common in the construction of dam, embankments, roadways, transport, highways, railways, and so on. Okay, so in this soil compaction, so we were familiar with another important relationship, that is called this dry unit versus the moisture content. So if we try to increase the moisture content, so what will happen? Initially, the dry unit weight of the soil sample will go on increasing, but it will reach a peak at some moisture content that is called as the optimum moisture content. Okay, so if we draw the relationship between dry unit weight of a soil sample versus its moisture content, so we'll see two different trends. Okay, so below certain moisture content, which we have defined as the optimum moisture content OMC, what will happen? With increase in moisture content, the dry unit weight of the sample will increase. However, once this optimum moisture content is exceeded, so if we add more water, or if the moisture content of the soil sample is still increasing in nature beyond the optimum moisture content, then we have noticed a decrease in the dry unit weight. Okay, so we have also learned, or we have also discussed what are the feasible reasons behind this kind of behavior, that we have discussed that time. Okay, while we were learning that soil compaction. Now we have also learned about different laboratory tests to determine the uh, or to basically uh, examine this kind of behavior, that is that are the this standard Proctor test. Okay, so two type of tests we have seen. And the standard Proctor test and the modified Proctor test, what is the major difference between these two tests, that also we have learned at that time. So in case of standard Proctor test, there are some standard specifications, means they should be the weight of fall, or the number of layerings, or the number of tampings. Okay, so these all are specified when you will be preparing the soil sample and testing the soil sample in the laboratory. So similar things will apply in the case of modified Proctor test as well. However, it's a difference that in case of modified Proctor test, greater compactive effort is basically applied as compared to the standard Proctor test, and as a consequence of that, basically the OMC will basically reduce, and the dry unit weight will basically increase. So a higher dry unit weight is basically observed at a lower optimum moisture content in the case of modified Proctor test compared to the standard Proctor test. Okay, now while we'll be trying to maintain this, or will be trying to ensure this laboratory condition in the field, that this much compaction or this much unit weight we should reach or achieve in the field. So what are there should be some terminologies, or there should be some indices through which we can understand, or we can realize, okay, so this much unit weight we have achieved in the field. So for that also we have some different types of test, or different types of specifications, standard specifications. So one terminology is there which we have defined as relative compaction. Okay, so relative compaction is nothing but the ratio of, so it's a ratio of that dry unit or dry density, uh, whatever we have raised in the field condition, and the maximum dry density which we have obtained from the laboratory condition. Okay, so in the field, if we obtain something in between 95 to 99 or 90 to 99, so we can say okay, the required relative compaction is basically achieved by means of the mechanical energy. Okay, so for imparting the mechanical energy, we have seen the uses of different rollers, which are uh, this vibratory roller, then ship put roller. Okay, so this type of rollers, we the application of this rollers we have learned from this course, and a particular type of roller will not be applicable to all types of soils. Okay, so it's not kind of a generalized application, so its uses will be specific. So it will be highly beneficial for a specific kind of soil, but it will not be beneficial for other kind of soil. So that also we have to keep in mind. And we have seen, so what are the types of soil, if this is the type of soil, then what kind of roller will be most suitable. Okay, now uh, proceeding further, we started learning another topic or another chapter of this course, that is called permeability in soil. So at the very beginning, we have seen that soil matrix, this is a kind of uh, solid particles, summation of solid particles and the pore spaces inside the soil particles. So this pore, when these pore spaces are basically interconnected, and since these pore spaces are basically may be filled with water or air, so what will happen, so there is a tendency that the liquid or the water which is basically inside the pore spaces, so that will basically tend to flow from high energy to low energy. So this type of behavior has been characterized by this permeability. So permeability, there is a famous law, Darcy's law, that is mostly used to characterize this kind of behavior, permeability in soil. And there are different tests by which we can determine the hydrolytic conductivity of a soil. So for example, there are constant head permeability test, falling head permeability test. So these are the laboratory tests mostly used to determine the hydrolytic conductivity of soil. Now, apart from this laboratory test, there are different field tests also, by which also we can determine the permeability, hydrolytic conductivity of a soil. So, to name a few, there are pumping out test. Then I think sand probe method is there. Okay, so determine the in situ hydraulic conductivity of a soil. Now, this hydrolytic conductivity of a soil can be affected by a variety of parameters. Okay, so this can be a parameter, this can be the properties of the grain size, properties of the soil particles, or properties of the permeating fluid. So please go through all these aspects, that what are the parameters which can affect the permeability of permeability in soil. Now, once we have the knowledge of permeability in soil, so under this heading, permeability on soil, we have mostly seen the flow in one direction, but this is quite idealistic. So to be more realistic, we have started discussing, or we have started learning the flow in the 2D condition, which means a more realistic simulation of the in situ condition. So for that, to define this kind of flow which is basically happening inside the soil mass, so we have taken the help of this concept of flow net. Okay, now what is flow net? Flow net, this is a basically network which is basically which consists of some consist of some flow lines and some equipotential lines. Now these lines are basically perpendicular to each other, Now this condition will be valid when we consider isotropic soil mass. Okay, so we have basically introduced a few terms, isotropic and anisotropic. So isotropic in the sense when the properties in a soil mass at a point are equal in different directions. But if this is not the case, that at a point the properties are basically varying with different direction or with directions, then the soil mass will be called anisotropic. Okay, so for the isotropic case, we have seen that the flow lines and the equipotential lines in a flow net meet each other at right angles. Okay, now this how to construct this flow net to get the flow, the amount of flow or the quantity of flow which is basically taking place inside the soil mass. So that are also basically covered in this course. Now this if the flow net is basically known to us for a specific application, for example the sheet pile, dam and so on, earthen embankment, then we can basically calculate a few things from the use of or from the concept of flow net. So first of all, we can basically calculate the rate of flow, that is the quantity of flow, and then we can also calculate the hydraulic gradient at different points inside the soil mass, then the uplift pressure beneath the hydraulic structure from the flow net, and also the factor of safety against piping, which we can calculate from or by constructing the flow net, or once the flow net is basically drawn for the given problem or for the given hydraulic structure. Okay, now moving further, we have learned different in situ stresses. In situ stresses means this total stresses, effective stresses and the pore water pressure. So for different conditions we have studied the stresses, in situ stresses. So one is if there is no flow condition. Okay, so flow is not taking place inside the soil sample, that is condition 1. And in condition 2, while the flow is basically taking in the upward direction through the soil mass. Okay, and for the third condition, flow is taking in the downward direction through the soil mass. So these are the three conditions for which we have studied the different in situ stresses. Okay, now depending on this knowledge or based on this knowledge of in situ stresses, we have learned about this condition of sand boiling or quicksand condition. Okay, so this is a very important aspect which is to be addressed or which is to be prevented. This is not desired at all from the practicality point of view. So if quicksand condition occurs, the soil will basically behave like a fluid, so effective stresses become 0. Okay, so this condition is basically will be governed when the flow is basically taking place in the upward direction. Okay, okay, now once this concept of effective stress was clear to us, so we have been introduced to another aspect of soil mechanics, that is consolidation. So while in the case of compaction, we have seen that compaction is a process of densification of soil mass through expulsion of air. Now in the case of consolidation, it is the case of expulsion of pore air from the soil matrix due to the application of some externally applied load. Okay, so this is the difference between, you can say this is the difference between consolidation and compaction. So in case of compaction, we are basically having expulsion of pore air from the soil matrix by means of mechanical energy. However, in the case of consolidation, we are having expulsion of pore air. Okay, so this under this heading or under this topic, we have basically learned how to calculate the consolidation and the time rate of consolidation. Okay, so this is a very essential aspect as a geotechnical engineer, because wherever you will go, so if you are dealing with the problems, soil mechanics problems, then you have to calculate so how much settlement a soil can experience in its life, and how much time will it take to complete this much of consolidation. So these are the two essential aspects of consolidation one should learn from this topic, consolidation. Okay, now This consolidation parameters can be obtained by different tests. Okay, so the standard test is the odometer test. Okay, so from the odometer test we can have a plot between the void ratio versus the effective stress. Okay, so if we plot the data from this test, uh, that is void ratio versus log sigma, so then we can have the idea of the compression index. Okay, and again you can basically get the coefficient of consolidation. So for that there are different methods reported in the literature. For example, time square root of time method, logarithmic type method. Okay, so you can use one of these to get the coefficient of consolidation, which will help you to determine the time rate of consolidation, and this compression index will help you to determine the total settlement which a soil can experience in its lifetime. Okay, so these things we have learned under this topic consolidation. Now after consolidation we have learned the shear strength of soil. So shear strength of soil, so this is basically defined by the linear mode Coulomb yield envelope. So the equation of this envelope is sigma n tan phi plus c. So this is the equation, tau equals to c plus sigma n tan phi. Now here phi and c, these are the shear strength parameters, and the objective was to determine these parameters. So there are different laboratory tests available by which you can determine these parameters, and under different conditions. Different conditions here infer that what is the condition of drainage valve. Okay, so throughout the test, so as you know that in case of shear strength test there are two phases. The first one is the consolidation and the second one is the shearing phase. Now if the drainage valve, depending on the condition of drainage valve, you can name this test. Okay, so for example, if the drainage valve is open throughout the two phases of a test, then you can say this is a consolidated drain test, means pore water pressure is not allowed to uh, accumulate inside the soil sample. So as the drainage valve is opened, so the excess pore water pressure which will be generated due to the application of external load, so that will be dissipated. Okay, so similarly there are unconsolidated undrained test, consolidated undrained test, then this unconfined compressive strength test. Okay, so these are the different categories of shear strength test by which you can determine the shear strength parameters. And while you will be implying or implementing this knowledge in the actual engineering, so you have to be very careful about the use of these parameters. So which kind of parameter you should use in the practical engineering, that is the undrained or the drained parameters. So you have to be very uh, decisive or very careful about the selection of these parameters. Okay, so these are the laboratory tests. Now coming to the field test, so we have seen the application of wind shear test by which we can determine the undrained position of the soil, and it is very useful for means soft to medium kind of clay. Okay, so the clay or very soft clay, which is basically uh, there is a high chance of remolding while we will be extracting this kind of sample for the laboratory testing. So in that case, the data or the parameters, shear strength parameters, which will be obtaining from the basically laboratory test, that will not be the actual. Okay, that can mislead us about the parameters which are exactly basically simulate the field condition, that can deviate from the field condition. So that's why we have to take the help of in situ test. So in situ test means by means of wind shear test we can also determine the shear strength of soil, and as I mentioned that this is very useful to get the shear strength parameters or undrained position of very soft to medium clay. Okay, now in this chapter only we have also learned the sensitivity and the thixotropy of soil. Okay, about the sensitivity and thixotropy of soil. Okay, now after shear strength we have learned about the earth pressure theories. Okay, so two types of earth pressure theories we have learned from this course. So first one is the Rankine's earth pressure theory, and the second one is the Coulomb's earth pressure theory. So there are some fundamental differences between these two theories. So for example, for the Rankine earth pressure theory, the wall friction was not considered. Okay, so the wall was basically considered to be perfectly smooth, but that is not the case in reality. So the Coulomb's earth pressure theory came into picture, and in the Coulomb's earth pressure theory, wall roughness was considered. Okay, so there are three kinds of earth pressures: earth pressure at rest, earth pressure under active condition, and earth pressure under passive condition. So we have learned to calculate all these kinds of earth pressure for different backfill conditions. So dry backfill, saturated, submerged, inclined, backfill with surcharge loading, layered backfill, and so on. And lastly, we have learned how to calculate stresses in soils by means of this Boussinesq and the Western theories. Okay, so in a nutshell, so this is a summary of the course. Okay, summary of the contents or topics which are covered under this course. Now we'll take a few numerical examples which were given or which were taken from the GATE examination 2024. Okay, so we'll see how this course becomes helpful to address these problems. Okay, so we'll first take this problem. So this is related to the index properties of soils. So an embankment is constructed with soil by maintaining the degree of saturation as 75% during compaction. The specific gravity of soil is 2.68 and the moisture content is 17% during compaction. Consider the unit weight of water as 10 kilonewton per meter cube. The dry unit weight in kilonewton per meter cube of the compacted soil is, we have to report this dry unit weight of the compacted soil after rounding up to 2 decimal places. Okay, so if we summarize the data which are given to this problem, so first of all, the degree of saturation is given as 75%. Okay, and the specific gravity of soil solids, that is GS, is given as 2.68, and the moisture content is given as 17%, and unit weight of water we can consider it as 10 kilonewton per meter cube. Now what we have to report? The dry unit weight of the compacted soil we have to report. So we know that dry unit weight, the formula for dry unit weight is GS gamma W by 1 plus E. Okay, now again this E, so there is no data for E. Void ratio is not directly given to this problem. So that means we have to calculate this E from the given data. So we know there is one famous relationship between these parameters, at least water content, specific gravity of soil solids, degree of saturation, and void ratio, like this, that WGS equals to S into E. Okay, so this is basically derived based on the index properties of soils. So WGS equals to S into E. So therefore we can obtain the E value from this modified equation, that is WGS by S. Okay, so we can substitute this expression now in the previous equation. So it will become 1 plus WGS by S. Now I hope all the parameters are known to us. Now just we have to substitute the appropriate values in this equation to get the dry unit weight of the compacted soil. So GS value is given as 2.68, gamma W 10 kilonewton per meter cube, water content 0.17, GS again 2.68, and the degree of saturation is 70%. 5%. That means 0.75. So if we calculate, so 2.68 into 10 divided by 1 plus 0.17 into 2.68 divided by 0.75. So it will be 16.67 kilonewton per meter. Okay, so this is the answer to this question. The dry unit weight of the compacted soil is 16.67 kilonewton per meter cube. Okay, so no such complication was there. So it's a very straightforward question. So once you know the expression for dry unit weight and the relationship between water content, specific gravity of soil solids, void ratio, and the degree of saturation, so you can easily answer to this question. Okay, now we'll take another question. So it's related to the permeability chapter. So a 30 centimeter diameter well fully penetrates an unconfined aquifer of saturated thickness 20 meter with hydrolytic conductivity of 10 meter per day. Under the steady pumping rate for a long time, the drawdowns into observation wells located at 10 meter and 100 meter from the pumping well are 5 meter and 1 meter respectively. The corresponding pumping rate in meter cube per day from the well is. So again we have to report this value after rounding up to 2 decimal places. Okay. So first we'll draw the problem statement. So this is the unconfined aquifer of thickness 20 meter. Okay, so this thickness is 20 meter. Okay, by the way, so this is an example of pumping out test to determine the hydraulic conductivity of a soil. Okay, so this test can be used to determine the hydraulic conductivity. However, for this problem, hydraulic conductivity is given. So rather, you have to determine the corresponding pumping rate. So for this kind of test, there is one test well, and in addition to that, there are several observation wells. Okay, for example, so in this problem, two observation wells are mentioned. Okay, so this figure is not to the scale. So this is the test well, and these are the observation wells. Okay, and this is the impervious base, below the unconfined aquifer. Okay, now due to this steady pumping from the test well, suppose this is Q. So what's happening? We have basically obtained a drawdown water table. Okay. So this is the drawdown water table. So similarly in this direction also, in this side also, we will have drawdown. Now okay, so this is the drawdown water table. Now this drawdowns into observation wells. Now these observation wells are located at a distance of 10 meter and 100 meter from the pumping well. Okay, so it would be better to rename this well as per the problem statement as pumping well. Now the distance between the pumping well and the first observation well is 10 meter. And what is the drawdown for the first observation well? The drawdown is 5 meter. Okay. Now coming to the second observation well, the distance between the pumping well and the second observation well is 100 meter, and the drawdown is 1 meter. Okay. So this is the problem sketch for problem number 2, and the Hardly conductivity of the soil is given as 10 meter per day. So we can solve this equation by recalling the expression of Hardly conductivity, which we can obtain from this kind of pumping out test. Now what is that expression? What is that expression? The expression is K equals to 2.3 Q log of R2 by R1 divided by pi H2 square minus H1 square. Okay. Now what are this R2 and R1? R2 and R1, so these are the distances of the observation wells from the pumping well. So R2 indicates the distance between the observation well 2 and the pumping well, whereas R1 indicates the distance between pumping well and the observation well 1. And H2, H1 represent the water level. So this is R2, this is R1, this is H1, and this is H2. Okay, so water level in the observation wells. Now if we substitute the values, appropriate values in this expression, then obviously we can get the value of Q. Okay, so before that we have to just rearrange this expression. So Q we can write as pi k H2 square minus H1 square divided by 2.3 log of R2 by R. Okay, so given the problem statement, R1 is 10 meter and H1 is 20 minus 5. Why 20 minus 5? Because the saturated thickness of the unconfined aquifer is 20, and for observation well, the drawdown is 5 meter. Okay, so this much water is basically there. So 20 minus 5, so that is 15 meter. Similarly, for observation well 2, R2 value is 100 meter and H2, this is 20 minus 1, is, and the hydroconductivity of the soil is given as 10 meter per day. So we have to substitute these values to get Q. So pi into 10 into 19 square minus 15 square divided by 2.3 log of 100. So it's 1857.64 meter cube per day. So this is the answer. Okay. So 1857.64 meter cube per day. Now, to answer this question, therefore, it's crucial to recall this expression of K, okay, which we can obtain from a pumping operation. Now, if this becomes the situation that we cannot recall this expression, then we can derive this expression from the fundamentals. Okay, so now we can have a look into the derivation process, how we can derive this expression. So for that, we have to basically consider a small tube, okay, a small tube of radius dr and height h, and at a distance of r from the pumping hole. Okay, so the hydraulic gradient from inside to outside K will be, I will be dH upon dr, and the area through which the flow is taking place it will be 2 pi RH. Now from Darcy's law, we know Q equals to K I A. Now if we substitute the Hardik gradient, that is dH by dr, and the value of area, cross section area 2 pi RH in this equation, then K, we can rewrite this expression as Q dr by r equals to 2 pi K H. Now if we integrate, have this expression, then it will become Q ln R2 by R1 equals to pi K H2 square minus H1 square. Therefore, K would become 2.3 Q log of R2 by R1 divided by pi times H2 square. So exactly what we have used, or what we have written in the at the beginning of this problem. Okay, so 2.3 times Q log of R2 by R1 divided by pi into H2 square minus. Okay, so this is for those who cannot recall this expression, so they can derive this equation and then substitute the appropriate values in this expression to get the value of pumping rate. So which we have got as 1857.64 meter cube per day. Okay. Okay. So if this is fine, then the next problem, this is in relation with earth pressure theories. Okay. A vertical smooth rigid retaining wall is supporting horizontal ground with dry cohesionless backfill having a friction angle of 30 degrees. The inclination of failure planes with respect to the major principal plane for Rankine's active and passive earth pressure conditions respectively are. So therefore, we have to report the inclination of failure planes with respect to the major principal plane for two conditions, which are Rankine active and passive earth pressure conditions. Okay, so this is the retaining wall. The angle of internal friction is 30. Now the failure plane inclination with respect to major principal plane, if we, okay, so two cases are there. The first one is the active case and the second one is the passive case. So in the active case, if we try to draw a typical soil element, so this horizontal and vertical surfaces, this will be the principal planes. Why? Because the surfaces are free from any kind of shear stress. So that means from the basic mechanics, a plane which is free from any kind of shear stress, that will be called the principal planes, and the stresses which are acting on this plane, that will be called the principal stresses. Now out of these principal stresses, the stress which is having the highest magnitude called the major principal stress, and the lowest one is called the minor principal stress. Now for the active condition, we must have the idea that which one is the major principal stress and which one is the minor principal stress. Okay, so for active case, the vertical overburden, this is the major principal stress, and the pressure, the lateral up pressure, this is the minor principal stress. However, in the passive case, so this is reverse. The vertical overburden is the minor principal stress, and the lateral pressure or the horizontal stress is the major principal stress. Okay, so for these two cases, we have to determine the inclination of the failure plane. So this angle, you can say, sorry, so this angle, because for this problem the horizontal plane is now the major principal plane, and for this case, this angle, because for passive condition the vertical plane is the major principal plane. So if we draw the stresses in the mode stress diagram, so this is the normal stress axis, this is the shear stress axis, and this is the yield envelope. Since this is purely cohesionless soil, so it will pass through the origin, and this angle is your phi. Now for both the cases, overburden at same point, the overburden will be constant, will remain same, so this will not change. So for example, this is the overburden, or this is the vertical stress. Okay, so here we can write bracket, this is vertical, horizontal. So active condition is basically attained when the retaining wall is basically moving away from the backfill, and as a result of that, so what's happening? So at that point, the horizontal stress is basically continuously decreasing, and a point or a situation will arise when the mode circle will basically touch the failure envelope. So this is the active state. Whereas in the passive condition, since the retaining wall is basically moving towards the backfill, so vertical stress remain constant. However, the horizontal stress is basically continuously increasing, and the situation will happen when this mode stress circle will touch the mode Coulomb failure envelope. Okay, now we can show this failure plane. So if this is the radius, if this is the radius, so from the point of tangency we can draw a line up to the center, and this is the Taylor plane, and this is rather we can say EP, this is PA. Okay, so this is your PA and this is your EP, and this is for example gamma z. Okay, so this is your gamma z. Now this angle, this 2 theta angle, can be obtained any of this triangle. So this value is your phi. So if you consider any of these two triangles, so 2 theta, this will be pi by 2 plus phi, or theta will be 4 plus phi. Please keep in mind that theta, which is the parallel plane inclination with the major principal plane in the the physical stress plane, now becomes 2 theta in the mode stress plane. Okay, however it's the same physical, it's bearing the same physical significance. So theta equals to pi by 4 plus pi by 2. This is the inclination, this is the inclination of parallel plane to the major principal plane, irrespective of the condition, that is passive or active. So it will not change as long as you are determining the inclination with respect to the major principal plane. However, if you try to determine this inclination with respect to horizontal or vertical, in terms of horizontal or vertical, then this values will change. Okay, so major principal stress orientation is changing from active to passive case. However, the inclination of the parallel plane with the about the major principal plane will not change. So what will be the value? So value will be, theta will be pi by 4 plus pi by 4 means 45 plus pi by 2, that is 2. Okay, so for both active and passive. So this is the okay. So these are the 60° and 60. Okay, so if this is fine, then we can take the next problem, which is problem 4. So in this problem, the total primary consolidation settlement SC of a building constructed on a 10-meter thick saturated clay layer is estimated to be 50 mm. After 300 days of the construction of building, primary consolidation settlement was reported as 10 mm. The additional time required to achieve 50% of the SC will be sorry. So the data which are given to this problem are the total primary concentration supplement SC, which is 50 ml. So this is the ultimate supplement the soil will experience. And after 300 days, so we can say T1 equals to 300 days. The reported primary concentration supplement S1 or SC1 is 10 ml. So what is the degree of consolidation? Then, so it's SC1 divided by SC, that means 10 by 50, 20%. Okay, this is 20% or 0.2. And this is happening after 300 days. So this is the T1. But we need to know the time for which this SC2 will be 25 ml. Why 25 ml? Because the degree of consolidation is mentioned as 50%. So U2 is mentioned as 50%. So SC2 50 into 50 by 100, so that means 25. Now one important thing which is basically missing from this problem statement, that is the coefficient of consolidation. Okay, without which we cannot proceed. So this is required. Coefficient of consolidation. CV. So this CV, if you read the problem statement very carefully, so this CV will be constant for both the scenarios because we are dealing with the same soil. We are not changing the soil, so this will be constant. Now if this CV is constant and we know the time factor TV, this is CVT by HD square. We know na this relationship. The time factor is CVT by HD square. So CV constant. What is T? This is the time which will be varying, which will vary depending on the degree of consolidation. And what is H here? H here, this is the drainage path then. So H here, this is the drainage path. Now, again, this parameter H here will be constant for this soil. Okay. So since we are basically dealing with the same soil, this drainage path length and CV will be constant. Now, if CV and H here will become constant, then what will happen for this expression? So this TV we can write is proportional to the time factor is proportional to time. So therefore, if we know the time factor, we can easily determine the corresponding time. So this will be the relation that TB1 by TB2 equals to 1 by T2. So if we know TB1, TB2 and T1, so we can easily calculate T2 as T1 multiplied by TB2 by TB. Okay. Now again, this TB can be calculated as pi by 4 u percentage by 100 square when u is less than 60%. Okay. Now for this problem, both the degree of consolidations are less than 60%. So therefore this TB1 and TB2, so this TB1 and TB2, so TB1, this is pi by 4 into 0.2 square, and TB2, this is pi by 4 0.5 square. Okay, and T1 is 3. So if we substitute, then T2 becomes 300 multiplied by 0.5 square, which is 1875. Now what is the additional time then? Because we have to report the additional time, okay, not the total time. So additional time delta T is T2 minus T1, 1875 minus 300 equals to 1575. Okay, so this is the additional time, 1575. So therefore it's very essential to notice each and every word involved in the problem statement. So we don't need to report the total time, rather we have to report the additional time which is required to achieve 50% degree of consolidation. So what we have done, so for that we have established a relationship between the time factor and the time, and we know time factor is a function of degree of consolidation. So once we know the degree of consolidation, we can determine the corresponding time factor. So from this expression, pi by 4 u percentage by 100 whole square, so this will be valid while the degree of consolidation is less than 60%. So, and this is true for the present problem statement. So therefore 20% degree of consolidation, the time factor is pi by 4 0.2 whole square, and correspondingly for 50% it's pi by 4 square root 0.5 whole square. So now if we substitute these values of TB1, TB2 and T1 in this expression, we'll get the total time required to achieve 50% degree of consolidation. However, we have to report the additional time, so therefore we have to subtract T1 from T2 to get the additional time, and which is 1575 days. Okay, so if this is fine, then we will take this problem which is related to shear strength of soil. So a soil sample was consolidated at a cell pressure of 20 kPa and a back pressure of 10 kPa for 24 hours during a consolidated undrained triaxial test. The cell pressure was increased to 30 kPa on the next day, and it resulted in the development of water pressure of 1 kPa. The soil sample failed when the axial stress was gradually increased to 50 kPa. The pore water pressure at failure was recorded as 21 kPa. The value of Skempton's pore pressure parameter B for the soil sample is. So we have to report the Skempton's pore pressure parameter B. Now what is Skempton pore pressure parameter B? So B, this is delta U3 by delta sigma 3. Now what is this delta U3? So this is the change in pore water pressure, change in pore water pressure in the consolidation phase. And this delta sigma 3, this is the change in confinement. Okay. Now for this problem, this delta U3 is reported as 1 kPa and delta sigma 3, this is 30 minus 20, that is 10. So if we substitute 1 upon 10, this will be 0. Okay. Now we can extend this problem further. So we can also determine the parameter A. Okay. So this is the homework. To all of you. How we can determine? So first we can determine the product AB from this expression, delta U1 by delta sigma 1. Now we know the B parameter already, so we can determine 1 upon B delta U1 by delta sigma 1. Now it's your task to find out the value of delta U1 and delta sigma. Okay. Okay. Now we'll take this problem of homogeneous earth dam. So a homogeneous earth dam has a maximum water head difference of 15 meters between the upstream and downstream sides. A flow net was drawn with the number of potential drops as 10 and the average length of the element as 3 meters. Specific gravity of the soil solids is 2.65. Now for a factor of safety of 2 against piping failure, void ratio of the soil is. So therefore, first of all, we need to know what is factor of safety against piping. So factor of safety against piping is nothing but the ratio of critical hydraulic gradient to the exit hydraulic gradient. Now what is I critical? I critical, this is the hydraulic gradient when piping failure will basically upward seepage force or the seepage pressure balances the submerged weight or the buoyant weight of the soil mass. Okay, so that means your effective stress becomes 0. Now at the beginning of this course, we have mentioned about 3 such conditions while we discussing about the in situ stresses. So no flow condition, flow in the upward direction and flow in the downward direction. Now when the flow is taking place in the upward direction, what will happen? The effective stress will be reduced. So we know that effective stress is a product of submerged unit weight and the corresponding height, suppose Z. Okay, so suppose if we draw the scenario or so if these are the two reservoirs connected to the bottom and top of the soil sample. So this is the soil sample. Okay. So what is the head difference between two soil sample? Between the two ends. So this is suppose delta H. Now what will happen? So flow will basically take place due to this head difference along the upward direction through the soil mass, because the total head which is available at the bottom is greater compared to that available at the top. So from bottom to top, the flow will basically take place. Now as a result, so what will happen? So if we basically measure the stresses, effective stresses at an elevation Z, Z now is basically measured from the top of the soil sample. So it will be gamma prime Z minus I gamma W into Z. So effective stress will basically reduce. Effective stress will reduce by this amount. This I gamma W is the seepage force per unit volume multiplied by the depth. So a time will will reach an instant while this sigma prime becomes 0. So if we increase the Hadley gradient, this I, so will reach an instant while the sigma prime value becomes 0. So that means this gamma prime Z minus I critical gamma W Z to 0. So therefore, we can write gamma prime minus I critical gamma W 0. Now what is the value of I critical then? I critical would be gamma prime by gamma W. Again we know gamma prime is nothing but GS minus 1 by 1 plus E multiplied by gamma W, and there was already gamma W in the denominator, so it will cancel out. So I critical becomes GS minus 1 divided by. So this is the critical Hadley gradient. Okay. While the effective stress becomes 0. Or the seepage force balances the submerged unit weight of the soil. Now what is I exit? I exit, this is the exit gradient Now this exit gradient is basically delta H by L exit. So the potential means the potential drop, okay. So the potential drop divided by the length of the last flow field adjacent to the embankment. Now, how we can determine this delta H? Okay, so this delta H might be confusing. So rather, we can write it as capital delta H. So this delta H we can determine this delta H we can determine by dividing the total head difference between the upstream and downstream side divided by the number of potential drops. So this is the head per potential drop. Okay, head difference per potential drop. So this is 15 divided by number of potential drops is 10. So this is the number of potential drops. So this is the head loss and this is the potential drops, number of potential drops through which this head is lost. So 15 divided by 10. So that means 1. And what is L exit? L exit, this is 3 meter, because as mentioned in this problem statement that all the element is having an average length of, okay. So therefore this delta H by L exit will become 1.5 by 3. So that means 0.5. Okay, so let me calculate here. So 1.5 divided by 3, that means 0.5, and this GS minus 1 by 1 plus E, so GS is 2.65. So this is 2.65 minus 1 with 1 plus E, that is 1.65 plus E. Now we know this factor of safety. This factor of safety is given as 2. So this value 2. So we can equate this 1.65 by 1 plus E. Okay, so first let me write down this factor of safety against piping is 2, or 1.65 by 1 plus E multiplied by 0.5. So 1.65 divided by 1 plus E, this is the critical hydraulic gradient, divided by 0.5, this is the exit hydraulic gradient. Okay, so 1 plus E equals to 1.65. E equals to 65. So this is the, so that means the void ratio of the soil is 0.6. So two things we need to know before answering this question. First one, the definition of factor of safety against piping, and that is the ratio of critical hydraulic gradient to exit hydraulic gradient. And then we need to know the definitions of critical hydraulic gradient and the exit gradient. Okay, so critical hydraulic gradient is when the flow is basically happening in the upward direction, and if we increase the hydraulic gradient, so critical value will basically will reach when the submerged unit weight will be balanced by the upward seepage forces. So at that time, the effective stress will become 0. So the critical gradient will be, the Hadley gradient will be critical. And for the exit gradient, so this is the ratio of delta H by L exit. So delta H, this is the head loss per potential drop, and L exit, this is the length of the average length of the exit flow. Okay. So from this ratio, we can easily determine the void ratio of the soil. Okay. Now we'll take the next problem. So in this problem, the in situ percentage of voids of a sand deposit is 50%. The maximum and minimum densities of sand determined from the laboratory test are 1 gram centimeter cube and 1.3 gram per centimeter cube. Assume the specific gravity of sand as 2.7. The relative density index of the in situ sand is. So you have to calculate the relative density. Now what is relative density index? So relative density index, RD, or this is, we can calculate from this equation, E max minus C divided by E max minus. So this is the relative density index. Now void ratios are not given corresponding to the loosest and densest and the natural state of a soil. Rather, the densities are given. So what we can do, we can basically determine the void ratios from the given data. How? That is it. Or rather, we can convert this equation into in terms of densities. So that will be, I think, much more convenient for us. So we know that gamma D, okay, so densities are basically mentioned. So rho D, the dry density, is GS rho W by 1, or we can write E equals to GS rho W by rho D. Okay. Now, while the rho D is minimum, so we will be having E max, and while rho D is max, we will be having minimum. So if we substitute this expression here, so what will happen? RT will become GS rho W by rho D minimum minus GS rho W by rho D. Now this 1 will basically cancel out, divided by GS rho W by rho D minimum minus GS rho W by. So if we further simplify this equation, so it will become rho D minus rho D minimum by rho D max minus rho D multiplied by rho D max by rho D. Okay, so this is the relative density index. So it's better to use this notation. Okay, so that means rho d minus rho d mean by rho d max minus rho d mean multiplied by rho d max. Now this rho d mean and max, these values are given 1.8 gram per centimeter cube and 1.3 gram per centimeter. So rho d max is given 1.8 gram per centimeter cube and rho d mean is given 1.3 gram per centimeter cube. Now what's about rho d? So rho d not given, rather we can calculate it from this equation gs rho w by 1 plus c, with which we have started solving this problem. Now gs, this is given as 2.7, rho w is 1 gram per centimeter cube, but what is e? So e, this is 0.5. No, this is not 0.5. So it's not void ratio. Rather, it's mentioned as in situ percentage of voids of a sand. Now, what is in situ percentage of voids? So it is VV upon V. So that means the porosity is mentioned in this problem, which is 0.5. So from this porosity, we can calculate the void ratio as n upon 1 minus n. That means 0.5 by 1 minus 0.5, that is 1. So rho d will become, so rho d will become 2.7 multiplied by 1 divided by 1 plus 1, that means 1.35 gram per. Now we can substitute the values in this expression. So rho d is 1.35, rho d min is 1.3, rho d max is 1.8, rho d min is 1.3, rho d max 1.8, and rho d is this. It will be 15.6. This is so either you can determine the void ratio values from the given data, that means the in the natural state, loosest and the densest state, then you can substitute those values in this expression Emax minus C by Emax minus C minimum to determine the relative density index of the sand. Otherwise, you can transform this equation in terms of densities. Then you can substitute the values of densities in the expression to determine the value of relative density index. Okay. So the second approach we have followed, and we have ended up with the relative density index as 13.33%. Check it once. The answer is 13.33%. Now we will take this problem. So this problem is again related to the shear strength of soil. So a drain traction test was conducted on a saturated sand specimen using a stress path triaxial testing system. The specimen failed when the axial stress reached a value of 100 kN per meter square from an initial confining pressure of 300 kN per meter square. The angle of shearing plane in degrees with respect to horizontal is. So again, in this problem also, so we have to determine the angle of shearing plane, which we have solved in one of our previous problems. So angle of shearing plane and angle of failure plane are both identical. So angle of shearing plane is theta equals to 45 degree plus 5. Okay, so this is the expression for angle of shearing plane. Now what we will do, will basically utilize the expression or relationship between sigma 1 and sigma 3 on the verge of polars. So we know that sigma 1 equals to sigma 3 tan square 45 plus 5 by 2 plus 2c tan 45 plus 5. Now as you know that this 45 plus 5 by 2 is theta, and the experiment or the traction test was conducted in a saturated sand, so therefore this theta, this c becomes 0. Therefore this sigma 1, so the modified equation will be sigma 3 square. So we need to only know the values of sigma 1 and sigma 3. So what is the value of sigma 3? So the confining pressure is 300 kN per meter square. Sigma 3 is 300 kN per square. So therefore sigma 1 will be this confining pressure plus the diabatic stress. So this delta sigma d is given as 100 kN per meter square. Sigma 1, this will be sigma 3 plus delta sigma d, because this is equal to sigma 1 minus sigma 3. Again, this is since drain traction test, so this sigma 1 to use this parameter in terms of drain, so it will be more appropriate. Okay, so this is sigma 3 and sigma both will be same, total and minus stresses in the drain condition. Okay, sigma 1 prime will be sigma 3 prime plus delta sigma d, so that is plus 100 equals to. So we can use the previous equation, that is sigma 1 prime equals to 100 tan square theta, and theta equals to root under 4 by 3, so theta will be straight 49.1. This is the so this is the angle of shearing plane with respect to the horizontal. Okay, so again you have to keep in mind that this relationship is valid only when you are determining the angle of shearing plane with respect to the major principal plane. And as you know that for triaxial system or triaxial sample, horizontal plane is the major principal. Okay, so we are determining this. Okay, so if this is fine, then we'll take the last problem for this session as well as for the entire course. So here two statements are given. So consider the statements P and Q related to the analysis or design of retaining walls. The first statement, that is P, statement P is, when a rough retaining wall moves toward the backfill, the wall friction force or resistance mobilizes in upward direction along the wall. So this is statement P. Now coming to statement Q, most of the earth pressure theories calculate the earth pressure due to surcharge by neglecting the actual distribution of stresses due to surcharge. So we have to check whether the statements are correct or not. So accordingly, we have to answer out of these four options. So both P and Q are true. So this is option A. Option B, P is true and Q is false. Option C, both P and Q are false. And last option is P is false and Q is true. So we'll check it one by one. So first we'll check the first condition, that is the direction of mobilization, the mobilized force, mobilized reaction force or the wall friction force for a rough retaining wall when the retaining wall moves toward the backfill. So this, a similar kind of problem we basically solved in the last session. So if you can recall from that, so if this is the wall movement, if this is the movement wall movement, the OH movement will be in the which direction? The OH movement will be in this direction. Okay, so this is the failure wedge. Now since the wall is rough, so the friction, so the wall friction force of the resistance, so we had shown earlier, so this will basically act. So that means we are dealing with currently the passive state. Okay, so it will basically act at an angle delta with the normal to the wall and above the normal. Since the wall is basically rough, so delta is not zero, so delta is having some non-zero values, and at the same time we have seen that this is the weight, this is the mobilized cohesion along the failure plane, and this is the reaction. Okay. Sorry. Yeah. So these are the forces and corresponding direction. So therefore, this statement P is false. Why? Because there it's mentioned that the wall friction force or resistance mobilized in upward direction along the wall. So that is not correct. So it will basically mobilize uh, with an angle delta and in the downward direction. Okay. So that means above the wall. So P, statement P, so this is false. Now coming to statement Q, so most of the earth pressure theories calculate the earth pressure due to surcharge by neglecting the actual distribution of stresses due to surcharge. Yeah, so this is true. Why? Because if you go back to the earth pressure distribution due to a surcharge, so suppose this is the wall and this is the retained backfill and this is Q. So what we have taken? So we have basically taken a uniform surcharge. Okay. So uniform stress multiplied by Ka as the lateral pressure. But this is not the situation if we consider the actual distribution inside the soil due to the application of Q. Okay. So that we can derive based on that theories, Westergaard Buzikness that we have seen in the chapter stresses in soil. So therefore, statement Q, this is. So we have neglected the actual distribution of stress due to surcharge. So we have basically taken the lateral earth pressure due to the surcharge as Q times K. So uniform distribution multiplied by the coefficient of earth pressure. So QK or Q. Okay, so that means P is false and Q is true. So first of all, when a rough retaining wall moves towards the backfill, the wall friction force or resistance uh, not mobilize in the doesn't mobilize in the upward direction along the wall. Rather, it mobilizes uh, with an angle delta to the normal with an angle del means at an angle delta with the normal to the wall and above the normal, that is in the downward direction. So that means statement P is not true. It's not correct. It's false. And secondly, that most of the earth pressure theories calculate the earth pressure due to surcharge by neglecting the actual distribution. So it's true. So P is false and Q is true. So option D is correct. So in this problem, we come to the end of this session as well as to this course. So before ending this session or concluding this course, so I would like to extend my sincere gratitude to Professor Priyanka Ghosh, who is the course instructor for this particular course, Geology and Soil Mechanics, and the NPTEL and PMRF support team for providing me this platform. And obviously, the course participants who have registered for this course. Okay, so with this, I wish you all the best for your end semester examination. So please practice the assignment problems and the problems which were solved in this problem solving sessions for a better understanding of this course. So I hope so you'll be able to address all the problems which will be basically which you will be having during the examination. I will wait for a few minutes. So if you have any further doubts or if you need any further clarification regarding any aspects which are covered in this course, otherwise I will end this session. And thanks a lot for being with me and for your active participation throughout the course. Okay, so I can assume that everything is absolutely fine from your end. So uh, again, best of luck for the end semester examination and thanks a lot. Have a nice day. Okay, so I am ending this session here.